like my capacity in making slides. So this is not about a paper I recently wrote. But what I wanted to do was to tell you about some of the connections and the tensions between some of the data we want in statistical estimation that you may or may not know about. These are recent works in the last 1 or 2 years. And sort of advocate for work to be done in 2 directions, which, I sort of know some things about, I'm interested in, but they're not my expertise. So here it goes. We'll start with covariance-aware Gaussian mean estimation, one statistical estimation task that has been very useful in helping us try to come up with broadly applicable new techniques. And we'll use this as the main example throughout the talk. What is this problem? It's we have an IAB sample drawn from a Gaussian distribution, mean mu, covariance sigma. We assume that the mean can lie in a potentially really big Euclidean ball of radius r, and sigma has some upper and lower bounds on its eigenvalues. What we want is, and we are in d dimensions. Oh, sorry, should people hear?
They can hear you from the other one.
Okay. And this is in d dimensions. And we want to find an estimator for the mean that has error alpha with probability 1 minus beta. These are the accuracy parameters. With respect to the Mahalanobis loss, this is what covariance aware means. It just means that we want the error in each direction to be proportional to the variance of the distribution in that direction. This is the formal definition of the Mahalanobis loss, but yeah, you should just remember the error should be proportional in all directions. So what do we know for this problem? Without trying to the empirical mean can give us a good bound. Specifically, we need d plus log 1 over beta over alpha squared samples in order to achieve this with the empirical mean, without that. And this hides a universal constant, but I'll try not to hide log factors, and I'll tell you when I do. Okay, so what are some of the resources that I'm considering in this case? One of them is sample complexity, the number of samples. The second one is differential privacy with parameters epsilon and delta, and we'll talk about both pure and approximate. Flashing the definition for completeness. The third one is robustness to data corruptions. So that's another thing that you might want from your algorithm. This definition, and we're going to stay a little bit longer. So what you might want is that if an adversary takes a fraction of points from your data set, an eta fraction of points, and it arbitrarily changes it, so it like poisons a few data points in your data set, your output still is quite accurate. So your output still has error at most this alpha of eta hyperprobability. But this hyperprobability takes into account both the randomness of the algorithm and the randomness of the initial data. So again, your algorithm formally is robust to a fraction of corruptions eta with failure probability theta and error alpha beta. It depends on the corruption level. If given a data set from a specific distribution, in our case, Gaussian, for all corrupted data sets up to eta n points, with probability 1 minus beta, the error remains at most alpha. Specifically for mean estimation, that we're talking, the problem that we picked today, this is roughly eta, or eta log 1 over eta. Robustness people think about etas that are constant. So you should be able to change a small constant fraction of your data set, n over 4 of your data set, and still do well. The other resources are time complexity, and there we're not going to be very specific, just polynomial versus exponential. And the fifth thing is not really, it is dependent on the sample complexity, but I'll explain why it's a different point in the next slide. But overall, I think these are the things that we're going to be considering for algorithms, like sample complexity, privacy, robustness, time complexity, and allowing for really small probabilities of failure and really small privacy parameters though. There's a ton of work in Gaussian mean estimation. If you know the covariance matrix, even covariance aware, if you don't know the covariance matrix, there's a lot of work. But these are the algorithms with the optimal sample complexity for the two pure and approximate DP notions. So the 2-key depth mechanism is achieving sample complexity that's D plus, this is the non-private term, this is the same in both cases. D plus log 1 over alpha epsilon beta over alpha epsilon plus D log R over alpha over epsilon in the pure DP setting. And there's the restricted 2-key depth mechanism, which replaces the last term with a log 1 over delta over epsilon. And it's approximate. Okay. So going back to the last point, allows for tiny beta and delta means that even if beta and delta are really small, the sample complexity does not blow up. So you can set delta to be e to the minus d, and asymptotically this term is not going to dominate. Of course, this trade-off we know, like we know that for pure differential privacy, we need dependence on the parameter bounds. For approximate, we don't. But if you're willing to relax to approximate, maybe you do want delta to be really, really small. So I think these are the reasons that I'm considering these desiderata for the moment. I don't know if you have objections, let me know. But yeah, we like this tiny beta and delta thing, and sometimes people call it the right accuracy guarantees or the right sample complexity for the problem, if you can achieve that. To be a bit more specific, if d was multiplied by log 1 over delta here, then setting delta to be e to the minus d would bring us a d squared term in the sample complexity. So that's what I mean. Doesn't blow it up because they're separate. Just a few words about these mechanisms. 2-key depth is a robust, very well known, 2-key median is a very well known robust estimator of the mean. And it essentially measures how central your point is to the data set. It says, if I take any half space that goes through the data set and through your point, how many points of the data set does it leave on either side? And if it leaves half of one side, half of the other side, no matter what half space you pick, then you're very central in the data set. In any case, the point I want to make is that all these mechanisms do is use the exponential mechanism to sample a point with high 2-key depth, which is known that it approximates the Gaussian mean very well. In the pure DP case, they do that over the ball radius r when you know the mean implies. In approximate DP, the algorithm is more complicated. The restricted exponential mechanism is more complicated, and we're not going to go into details so much. But it's a similar mechanism. It's the exponential mechanism, sampling a point with a 2-key depth score function over some other restricted set, not the radius r ball. So great. These mechanisms achieve the optimal sample complexity, but neither of them is polynomial time. At the same time, they are both robust. 2-key depth is robust, and so these mechanisms are robust as well. So you may ask at this point, okay, what about polynomial time? All is great except for the time complexity. The first algorithm with this optimal, well, we didn't know. I guess we don't know. The best sample complexity for this problem in approximate BP has this sample complexity, which is d times square root log 1 over delta over alpha epsilon plus d log 1 over delta over epsilon. So polynomial time, but we lost the tiny beta and delta assumption or like requirement.
You see where that is,
Yes.
because they're also in log terms.
They're all in log terms.
Yeah.
Yes, use it. But if you want to set it to e to the minus d, it's gonna give you a d squared sample complexity. So it's just gonna just because they're multiplied instead of added. So, and we also don't know if it's robust. So the question is, what can you do in polynomial time? I was gonna take a detour and tell you about the whole relationship between robustness and privacy. I'm gonna do it really fast because all I'm going to say is that you can go from one to the other. We know that any robust algorithm can be transformed into a private algorithm. And this transformation gives us an extra, for mean estimation, for example, if you take a robust mean estimator, you can transform it into a private mean estimator. With the sample complexity is actually optimal, like the one we saw before. The transformations are often optimal. They work for epsilon and epsilon delta. And sometimes they're polynomial time. The other way around is also true. Any private algorithm is also robust to a fraction of corruptions. So here we are. The fraction of corruptions that a private algorithm is robust to is log 1 over beta over epsilon n, or whichever is smaller, log 1 over delta over epsilon n. So if you have pure dp, only the first term matters. You have approximate, you can consider the second term. Okay, so for this thing to be a constant fraction, for eta to be a constant fraction, I want beta and delta to be really, really small. So the algorithm, the private algorithms for which beta and delta can be 2 to the minus n, these will give me fractions of corruptions, the robustness to fraction of corruptions that's a constant. This is where this beta and delta being very small comes back at, and this is maybe where the term right accuracy guarantees might have been. Okay, so back to our question. Can we have a differential private polynomial time estimator with tiny delta and beta? This would mean that we have a robust estimator with the same sample complexity because of this previous result. We'd have a robust estimator to a constant fraction of corruptions. And here comes the negative result. On New Year's Eve, I kids have nothing better to do. This paper shows some evidence that this is hard, pretty strong evidence, I suppose. The conjecture necessarily doesn't matter exactly, but basically, okay, I'll tell you what the conjecture is. So they show that, yeah, this paper shows low degree hardness of covariance aware robust mean testing. And this is based on something that people in robustness use a lot, the non-Gaussian component analysis problem for lower bounds. if you don't know what low degree lower bounds are, you might know what statistical query lower bounds are, and this is we're close to that. In any case, this lower bound says that we think that it's unlikely that you have an eta robust estimator for covariance aware Gaussian mean estimation with fewer than eta squared v squared or less samples. And back to what we were talking about, this means that any polynomial time epsilon delta dp estimator will either use, thank you, will either use d squared samples, or d has to be multiplied with log 1 over beta, d has to be multiplied with log 1 over delta. So, you know, this is not, you can try to come up with polynomial time robust estimators that overcome these lower bounds, but I trust the robustness community to some extent that this is really hard. So back to where we were, it's probably unlikely that you can decouple these terms unless you pay d squared in the sample complexity. So I think that's an understanding that I think is generally useful to, yes.
Can I just ask, I don't want to slow you down, so.
No,
Like polynomial time in what?
N and B.
And the other parameters,
I think, oh.
like epsilon, delta, beta,
No, 1 and 1. Sorry, delta, I don't. Epsilon 1, accuracy 1. The lower bound, these are fixed in the lower bound.
and then the beta and epsilon are. Beta and delta.
Epsilon is 1. Beta and delta should be unconstrained, I think.
I guess, okay,
Sorry.
I'll ask you.
Does it preclude some really bad beta?
Yeah, it's like,
Yeah.
this is more.
Maybe there's an upper bound to it, like cover.
Yeah.
Okay, sorry. Yeah. It's an 84-page paper posted on New Year's Eve. Like, I'm not sure what the parameters are, but yes.
I mean, it's,
Yeah.
they may have started writing it for.
Yeah, but I didn't get to read it. Sorry. Okay. So, I had another whole thing I wanted to say. I'm gonna go to the end and first say, okay, so the one thing I wanted to sort of point to is that if we think we know the techniques for statistical estimation and we start thinking about polynomial time and we want them to make it to be more practical and so on, we might want to look into these information computational gaps that exist, either to come up with new ones, or I would personally look at robustness and try to import from there. Covariance aware Gaussian mean estimation is not the only problem where this happens. I at least know about linear regression as well, and I think there are more. Maybe learning the covariance in operator norm has similar gaps in robustness. So maybe you can import more things from there and have a better understanding of what limits we have in private estimation. The whole second thing I was going to talk about, but I'm going to point to it, is other than that, 2D depth mechanisms check all the boxes except for polynomial time. So why are they not more popular? So we tried to implement, well, they're not popular because you need n to the d squared time to compute the volume of 2D level sets and sample using the exponential mechanism. But we tried to implement 2D depth mechanisms. No, we didn't try, we did. And the thing we can trade off, so I can talk about the implementation offline. This is work on the practical side that we recently did with Gavin Brown. But what I wanted to say is that the other thing you might consider is trading off some of the affine invariance. So instead of coming up with a 2D high point of high 2D depth, maybe you'd want to consider a variant which is called random 2D depth, which is a fine invariant if you pick enter the D directions. But in practice, if you just pick D directions, it's not too bad. So it roughly gives you good accuracy. And there are some studies about this and some reasons why it's might be. Okay. But the point is, K is a way to trade off computation for accuracy. So your computation becomes N K to the D, and your accuracy increases as K increases. So maybe new ways to that. Okay.
The question for this, we already had some. You can tell. The next speaker is Lydia.
Yes, I think.